Hi, let's talk about the first exam here in spring 2021. We had four items that you were addressing, and most of them just had a couple of parts. The last item was really a series of short answer questions. All right, so in the first item, we had a two-span beam. You looked at material being staged only on one span. You were first asked to determine the statical classification. Is it determinate, indeterminate, or unstable? Of course, it turns out we have four independent reaction components, only three equations of equilibrium, no special conditions of equilibrium. So therefore, it is statically indeterminate to the first degree. From an external perspective, what that means is that it's possible that one of the redundant reactions, in this case, that would be one of the vertical reactions, could potentially fail, and we might be able to redistribute loads. Probably not in this particular scenario, but that's the theoretical meaning of that redundancy. The tributary model here would suggest to us that we just take the load in the left span from A to B, half of it goes to A, half of it goes to B. And of course, the reaction then at C would be zero. The tributary model is really isolating these spans from each other, whereas the continuity that's created by a single beam being placed all the way over the entire length would mean that there actually is some effects that are communicated from each span or to the other span. And that's what we are after in part C is, okay, if it is continuous all the way through with these loads, now what do we think happens, right? And so imagine you place the load there on span AB, that's going to want to make that part of the beam want to sag into a smiley face. However, the continuous nature there at point B of the beam means that the span BC wants to rotate in a counterclockwise fashion. It can't do that though because the support over at C is anchoring it or holding it down. So therefore, the reaction at C will be down, and that's going to mean that B is sort of a fulcrum, and it's going to get bigger, whereas A is going to get a little bit less. In part two, we're taking a look at the lateral resisting systems and a 30 pounds per square foot lateral load that's applied to this system, right? And from a wind source. In the first case, we're asked to draw the lateral resisting system, or really the frame that is, in line 3. The little triangles there in the beam that goes from B to C indicate that those are moment connections. And the fact that we don't have those in the other span from A to B means that those are shear axial only connections. So when we draw our model, we're going to have, of course, two stories. We'll have pins for the supports, because that's what we were told that was happening at A, B, and C. And then we have two stories, and we have a moment frame that is over on the left side, meaning the BC side, and from A to B, we would just have hinges on each end of the beam. Do not put the hinges in the column. We don't like hinges in columns. That tends to create some instability concerns when we do that. So the column would be continuous over those two stories, is what that means. In part B, we're looking at those loads that get applied there, the 30 psf, to that broadside view of the eastern face. Now note here, the critical thing turns out that you've got along frame line C a 2-bay moment frame, as you do also in line A, but in line B there are no moment connections in the direction of loading. Right? Remember, these systems are like sheets of paper, and they have no stiffness out of plane. So whatever's going on column line 1, 2, or 3, it's not relevant here. It doesn't play a part. And so with frame B not being a part of the lateral force resisting system, then whatever the lateral loads are, they get distributed by effectively tributary action over to line A and to line C. From dimensionally, what you do have to keep track of is that there is a 1-foot overhang on either side, so you do end up with a 16-foot tributary width for the frame line A, as well as actually frame line C, right? And then back up here for the elevation tributary heights, you've got the 3-foot parapet plus half of the upper story, and then half of that goes down and half of the bottom comes up. That would be a 12-foot, and then 7 foot down to the lowest level. If you had wanted to, you could have used sort of a diving board that went from L1 all the way up to the top of the parapet. It's a little bit more accurate than the tributary model. For the exam, it was just fine if you used the tributary only model. In 3, we're looking at really load patterns on various members. And so the first thing we ask is whether this slab that is in the area between B to C and lines 2 to 3, whether that's a 2-way or a 3-way slab, given that this is the only part of the structural system that we see, these dark lines, right? And you have the slab. Well, in that case, the slab is going to try to behave in a 2-way situation if it is supported on all 4 edges, and it is, and if the aspect ratio of the long side to the short side is less than 2 to 1, then it's going to be effectively 2-way slab action. If it is larger than that, you can actually fairly reasonably model it as 1-way, but we don't have that here. This is going to be a ratio of 25 to 20, so 1.25 to 1. It's going to be a 2-way slab action. Now in part B, you were asked to look at this beam that goes right along the side of this elevator and stairwell opening, and over here in the far right bank, along line B. And that beam is going to take some sort of load from the span or the slab that's just to the north of it, as well as something coming from the slab that is just to the south of it. Those two are also going to turn out to be 2-way slab type behavior for the same reasons that the other one was. And you're going to find that they're on the short side of this rectangle that is the slab, and that means that you're going to end up with a triangular load coming into the beam that is of interest. You're going to have 2 different triangular loads, one that goes over the whole 15 feet and one that goes over only the 9 feet from either side of the beam. And you have the self-weight, that'll be a uniform load, and you'll have the reaction that comes from the beam that is on the 3.1 beam line. That's one that a lot of people oftentimes neglect and forget to include. We were looking for the load pattern here, not for the total amount of load. Right? We just wanted the tributary dead load that would be imposed on to the beam as we create the model for beam B3, B4. All right, so and then the last item, we had a series of short answer type of questions. The scenario was a pavilion that looked very similar to this one here. It has this sloped roof, has a whole bunch of frames with these flourishes that are the flourishes are the knee braces for each of these portals, right? And we were going to do a zoom in, a close-up look at that bottom joint on that truss. We see this decorative plate that is also a connecting plate for the system. And the questions were of a varied nature, but on the first part was, how should we model these connections? Ignore the problem statement said, ignore the braces that came in here. This is a king post truss, and so we're ignoring them. We're only focusing on the post and the bottom cord. The post frames in and is one solid piece of wood, or really what we call timber, and then it's connected here by these 2 bolts to the T-plate. The T-plate is on either side of this member, and that tells us when the bolts there are only not at the outer fiber. There's nothing there connecting where sigma equals my over I would be largest. So even though there could be a force coupled transfer, it's not going to be very significant. And oh, by the way, you're going to have clearances that are going to be needed to get those bolts through there. This thing is not going to have a lot of restraint to rotation. So for sure, there would be a pin connection of this king post as we model it coming into this joint. Now you would make the same argument for the bottom cord. However, note that the bottom cord is continuous all the way through. And that means it's going to be modeled as a rigid connection to the joint at that location, right? So that was part A. Now part B asked, well, what kind of risk category should we use here for design purposes? Well, the thing is that even though this is an open structure and you might think there's easy ingress and egress, that is not a part of the analysis here. Risk category is relating to the risk to human life, not to an individual human life, but then almost an occupancy type of category. This is going to, if it's seating 100 to 150, that's starting to get pretty significant. And that's why it's going to fit into risk category 2. If it was 300 people, you'd start to see that it might be actually better to call it risk category 3. Risk category 1 is really for unoccupied spaces, and we don't have that. Yes, at times it's unoccupied, but so are commercial buildings unoccupied at 2 or 3 a.m., with the exception of maybe some cleaning staff, right? So it's not about what the situation is in its easiest kind of scenario. It's, hey, this system is meant for an appreciable number of people, and there's no way we want to call it risk category 1. Now, if you only have 10 people there, there's an interesting question of, well, should that be risk 1 or risk 2? Probably going to err on the side of calling it risk category 2, most likely. If it's only 3 people, now you're really starting to make it kind of an interesting debate, but you know something, you're probably still going to call it risk category 2 because it's meant for human occupation. You're not talking about something that is meant for the pigs and the cows. All right, so part C then is determine appropriate design wind speed for this structure. We have an address. It's in sort of downtown Salt Lake City. It's really not downtown per se. It's really out by Sugar House. And so we put that into our ATC hazards map, and that will be 103 mile an hour. Now, if you look at the current applicable Salt Lake City design criteria from the Salt Lake City building official, you will find 105 mile an hour. That's historic. What we used to have was only wind speed maps. They were map or wind speed contours at every 5 mile an hour increments. So it's a little bit historic to go from 103 to just bump it up to 105. If you selected 115, there's a good chance you were looking at an outdated set of criteria, and that was associated with residential construction, which this is not. This is a public structure. So you got to be a little careful of what sources you pull from. If you even pulled an older one, you might have seen 90 mile an hour, which really dates back more than 10 years. For the snow load, what you'll find is that if you try to go to ATC hazards, they'll say, nah, you're in a mountain area, so go somewhere else. That's what they say. So like we talked about in class, you go to the USU snow load map and their web browser, and they'll again put in the address. You'll get back 31 pounds per square foot. If you go to the current Salt Lake City design guide, they'll tell you that the minimum is 28, but then what you got to do is go to the Utah snow load, and you'll find out that 31 is the appropriate one to use. All right, so that's the current 2018 based criteria from the city. Again, you got to be careful both how you read these things and which ones you pull. The real problem is that a lot of these things are still out there, even though they're old and not applicable anymore, and sometimes are very poorly dated. S is the one that actually says ASCE 7-16. I don't know what they were talking about because it does not conform with the true ASCE 7-16. I suspect it dates to 2016 for using ASCE 7, which at the time, the applicable one was probably ASCE 7-10. Oh, drives you nuts, right? And it's why the building officials need to be so careful how they date these documents. They can't do a lot for the servers that are out there that have cached files because they don't control those caches. But they can control much better about what they do with their own information, which sometimes they still don't document them very well. It can be confusing, there is no doubt. The roof live load here would be 20 PSF. A lot of people were choosing 100 PSF because they saw that this was an area of assembly, and therefore they saw an ASCE 7-16 table 4-3.1 and went down to roofs and saw that, oh, for an area of assembly, that would be 100 PSF. No, right? We're not assembling on this structure, are we? So even if we call it a flat roof, for the purpose of this exam, we're still not assembling on it. So therefore, that's 20 PSF. Now, if you go through for sloped roofs, you can actually get a reduced value, but 20 PSF would be the starting point for our situation. And then finally, we've got the probability calculation here. We've got the target annual failure likelihood of 5 times 10 to the minus 6 per year for a sudden or potentially widespread damage failure mode for a risk category 2 structure. And so what that means is for a recurrence interval, all we do is take the reciprocal of that. That's 200,000 years, right? So on average, we want that kind of situation only happening one for 200,000 years, a very low likelihood. Now, 50 years tends to be oftentimes what we base our periods out of, and it's sort of a reference period. And so that's why the number 50 is thrown down here. So what's the chance of failure that we'll have if this is our annual likelihood of failure? What's our chance of failure in 50 years? Well, okay, so our chance of success is not 5 times 10 to the minus 6. That chance is 1 minus that. That's something like 99.99995% chance, something like that, right? It's 1 minus that 5 times 10 to the minus 6. So that's our chance of success every year, meaning no failure. And so then all we do is we just multiply that times itself 50 times, right? We're going to roll the dice, and we have a 1 minus 5 times 10 to the minus 6 chance of being just fine every year. So roll the dice 50 times and see what you come up with, and it's pretty extraordinarily high, 99.9. What is it? Well, let's just check it out real fast. Here, 1 minus 5 times 10 to the minus 6, so 99.95, okay? And we're going to raise that to the 50th power. There we go. That's right, 99.975% chance of good things happening for us. Okay, so that's what's going on in the test. And I don't know. Keep on moving on, I guess.